So, we are discussing the Maxwell's equations in the relativistic case. Maxwell's equations written in a normal way in terms of the electric and magnetic fields, that itself is as I said Lorentz invariant, but we could write yesterday in a more compact way the Maxwell's equation, two of the Maxwell's equations in fact, and the way we had written that, it is clear, the Lorentz invariance is clear in that. Now, today let us continue our discussion on this and see how to take care of the other two equations. So, let us consider the object that we had introduced yesterday. Now that we are familiar with this, we will I will call this the field tensor F mu nu. We did not introduce or call it by any name yesterday, so but it is usually called the field tensor. It is a second rank tensor, and in the matrix form we can write it as 0 minus E x minus E y minus E z, E 1 0 minus B z B y, E 2 B z 0 minus B x, E 3 minus B y B x 0. So, this is what we had written down yesterday, and properties are that F mu nu is equal to minus F nu mu, antisymmetric under the interchange of these two indices mu and nu, and that we said it is a second rank tensor. So, therefore, it is actually going to transform in a like a second rank tensor. We will come to that maybe at some other point of time, or it is not important here. Let us see how do we write down the lower components. Let us look at the covariant form of this tensor F mu nu. So, we have to lower two of these indices if you want to write it in terms of the contravariant tensor. So, F rho sigma, so will connect with F mu nu covariant in this fashion, G mu rho G nu sigma. This is very similar to the raising and lowering of the indices of vectors, covariant to contravariant and contravariant to covariant. But then this let us see what are the components of F lower ones. So, 0 0 or the diagonal elements are all zeros. So, it is still antisymmetric with respect to the interchange of these two indices. So, the diagonal elements are zeros. Of diagonal elements, F 0 1 is equal to G 0, mu is fixed to be 0, right, and nu is fixed to be 1. So, I can write it as G 0 rho, G nu is now 1 and sigma is anything F rho sigma, rho and sigma are summed over. But we know that G is a symmetric diagonal metric. So, if one component is one index is 0, the other index is also 0 for it to be non-zero value. So, G 0 0 is 1 and G 0 with any other index. So, if rho is not equal to 0, the first G, the component of the first G is going to be 0 then. So, therefore, the only non-vanishing term that you will get here is G 0 0 and sigma equal to 1. So, rho equal to 1, sigma equal to 1. So, this is rho equal to 0, sigma equal to 1. So, F 0 1 lower indices is related to F01 upper index with the same indices, the upper and lower cases, and this is equal to G00 is plus 1, G11 is minus 1, therefore, altogether there is a minus sign. F02 is similarly minus F02, F03 is minus F03. We will now consider mu equal to 1 and nu is either 0 or 1. So, if it is 0, 1, 2, 3. So, F10 is equal to G11, G00, F01, which is equal to again minus F01. In fact, since it is antisymmetric with the interchange of these two elements, we do not really have to write this down at all. We can get it from F01. So, we will not write the rest of it. The 1, 2 element is nu. So, 1, 2 is G11, G22, F12, and both G11 and G22 are minus 1s, therefore, together they will give a plus 1, and therefore, the sign is not changed in this case. Similarly, for F13, which equal to F13, and you can see that F23 is also equal to F23 contravariant. So, altogether we can write the matrix F mu nu covariant as 0, there is a sign change there, so Ex, Ey, Ez, again similarly for the first column minus Ex, minus Ey, minus Ez. Diagonal elements are zeros. In the case of off-diagonal elements in the second or belonging to corresponding to the magnetic field, there is no change in the sign compared to the contravariant case. So, it is Bx minus Bz By plus Bz in the third row minus By in the fourth row and 0 diagonal plus Bx here minus Bx here and a 0 in the diagonal term. So, this is basically the covariant F mu nu. So, between contravariant and covariant F mu nu, the electric field components change sign and magnetic field components remain the same. That is easy to consider. Another object which we will denote by F tilde mu nu equal to epsilon mu nu rho sigma F rho sigma covariant with a half factor. Here epsilon mu nu rho sigma is defined in this fashion. F epsilon 0, 1, 2, 3 is equal to plus 1 and it is fully antisymmetric. What do I mean by that? Meaning interchange of any two indices keeping the others at their positions will give you a minus sign. That is, for example, epsilon, if I interchange the first two, I will get 1, 0 keeping the third and fourth at the same position, 2, 3 is equal to minus 0, 1, 2, 3, or it could be 0, 2, 1, 3, where I have interchanged 2, 1, 1 in epsilon 0, 1, 2, 3. So, I get a relative minus sign, etc. Let us look at F tilde mu nu. Clearly, if mu is equal to nu because of the antisymmetric property of epsilon mu nu rho sigma. If both of them are the same, if any two indices are the same, that will give you a 0. That is the only way, because one object will be, say for example, if I take epsilon 0 0 1 2, that is going to be equal to epsilon interchanging this to this and this to this, first and second will give me the same thing, epsilon 0 1 2 3. But we already said that interchanging any two should give you a minus sign. So, that will give you consistent solution as a 0. There is no other way that you can get anything equal to minus 1. Only way is to set it to equal to 0. Therefore, f mu nu is equal to 0 for mu equal to nu, and it is antisymmetric with the interchange of mu nu, because epsilon mu nu rho sigma is antisymmetric with the interchange of mu nu. Now, let us get the components. F tilde 0 1 is equal to half epsilon 0 1 mu nu f, all right. So, f tilde 0 1 is equal to half epsilon 0 1 rho sigma f rho sigma. Rho and sigma are summed over. Now, we see that since epsilon already has fixed two of the indices 0 and 1, rho and sigma can take the rest of it, rest of the indices, which are 2 or 3. So, it can, when I set rho equal to 2, sigma can take only one value, which is 3, because we cannot repeat the indices. So, here rho is equal to 2, sigma is equal to 3. Add this to other possibilities. So, that is what you mean by take summation over rho and sigma. What are the other possible rho values? We have taken one possibility, which is 2. We cannot take 0, we cannot take 1. So, the other possibility is 3. Once you take rho equal to 3, sigma is fixed to 2, f 3 2. But that is equal to epsilon 0 1 2 3 f 2 3 minus epsilon 0 1 2 3, because epsilon 0 1 3 2, if I interchange 3 and 2, it will pick up a minus sign. So, that is equal to minus of this f 3 2. But I will do the same thing with epsilon same thing with f 3 2 as well, 0 1 2 3 f 2 3. When I change f 3 2 to f 2 3, that will pick up another minus sign. So, making it plus epsilon 0 1 2 3 f 2 3. Now, these two are the identical terms, and together that will give me epsilon 0 1 2 3 f 2 3, which is equal to 1 factor of 1 for epsilon 0 1 2 3, and f 2 3 is the covariant f 2 3, 2 3 is minus bx. So, it is minus bx. Now, you understand why we had taken a half factor there. It was in anticipation that we had put a half there, so that we can get a minus bx without any two factors there or any other factor. In a similar fashion, you can actually do your homework and then get f tilde 0 2 as minus by, f tilde 0 3 as minus bz. Okay? And f 1 2 tilde is equal to half epsilon 1 2 rho sigma F rho sigma equal to half epsilon 1, 2 are fixed. What are available? Rho could take 0 or 3. Let us take it to be 0 to start with. Then sigma is 3. So, F 0 3 plus epsilon 1 2 3 0 rho equal to 3, the other possible value F 3 0, and that gives us epsilon 1 2 0 3 F 0 3, and epsilon 1 2 0 3 is minus epsilon 1 0 2 3, where I have interchanged 2 and 0, the second and third indices, which again to get into a form epsilon 0 1 2 3 I have to interchange 1 and 0 first two indices. So, that will give me a plus 0 1 2 3 F 0 3, which is equal to factor of 1 for epsilon 0 1 2 3 and F 0 3. F 0 3 is E Z. So, this is equal to E Z. Similarly, we can get F tilde 1 3 as minus E y and F tilde 2 3 as F E x. The rest of the terms are all obtained by taking the interchange of the indices from whatever we already have. So, putting it together, I have F tilde mu nu equal to 0 minus b x minus b y minus b z b x 0 E z minus E y b y minus E z 0 E x b z E y minus E x 0. Let me also write down F tilde F mu nu alongside. F mu nu we had 0 minus E x minus E y minus E z E x E y E z 0 minus b z b y b z 0 minus b x minus b y b x 0. So, you can see that we can get one from the other. How do you get one from the other? F tilde mu nu is obtained by taking, or let us do the other way. You start with F mu nu, change E to B, all the components. So, wherever you have an E x, you replace it by B x, E y goes to B y, E z goes to B z, and wherever you have a B x, you change to minus E x, and E y to minus E y, E z to minus E z. So, that will give you F tilde mu nu, or the other way around. With this, let us take F tilde mu nu, take the fourth derivative of this, set it to equal to 0 to start with, and then that will give you as an exercise. This is an exercise, divergence of B equal to 0 and minus curl of E is equal to dou B by dou T. You will recognize this or these two as two of the Maxwell's equations. So, together with the earlier dou mu f mu nu equal to j nu, dou mu f tilde mu nu equal to 0 for any nu give you divergence of E is equal to 0, divergence of E is equal to rho, divergence of B equal to 0, curl of E equal to minus dou B by dou T, curl of B which we got earlier is equal to J plus dou E over dou T. This is a compact way of writing the 4 Maxwell's equation in a covariant and an explicitly or covariant fashion, or Lorentz invariant fashion, I mean Lorentz covariant fashion. So, this is what we have, and going on, just one thing to notice here, J nu is for vector with first component or 0th component equal to rho and the charge density, and 1, 2, 3 component equal to the current density. Alright. So, let us come to expressing the field now in terms of the potential. We know we can write electric field as gradient of scalar potential and time derivative of vector potential. The first term is the electrostatic field and second term corresponds to the dynamic electrodynamic term, or which is due to changing magnetic field. The first term is curl free and second term not necessarily curl free. Curl of the second term is going to give you the variation in the magnetic field. Curl of A is magnetic field E. So, that is what we have for B. B is curl of A. So, if we have a time changing, time varying electric field, magnetic field, that will induce an electric field which is given by this. Let us focus on the electric field expression. Let us denote the electrostatic field potential phi and the vector potential A together as a 4 vector. We can call it the 4 vector potential. Okay. And we already know dou mu is equal to dou by dou T minus gradient, dou covariant is dou by dou T plus gradient. So, now let us look at the E x. So, let me write that again for the general one. E is grad phi minus dou by dou T of A. E x is, let me first write the derivative term, minus dou by dou T A 1 or A x minus grad dou by dou x A 0. So, this is equal to minus of dou by dou T is dou 0 A 1 minus, so now it should be plus dou by dou x is actually minus dou by dou x is dou 1. So, we have dou mu equal to dou by dou T which is dou 0 and minus grad. So, there is a minus sign. So, there should be a minus sign here. So, we have dou 0 A 1 minus dou 1 and A 0, which is equal to minus dou 0 A 1 minus dou 1 A 0. But if you look at the field tensor f mu nu, the zeroth mu equal to 0, nu equal to 1 will give you minus E x. So, taking f 0 1 as minus E x gives us dou 0 a 1 minus dou 1 a 0 as f 0 1. In a similar fashion, you can get 0 2 as dou 0 a 2 minus dou 2 a 0, f 0 3 as dou 0 a 3 minus dou 3 a 0. Okay. Now, let us switch over to B is equal to curl of A, B equal to curl of A, B x is equal to dou by dou y a z minus dou by dou z of a y, which is equal to minus dou 1 dou 2 a 3 minus of minus plus dou 3 a 2. Since we know f 2 3 is equal to minus b x, we have that equal to dou 2 a 3 minus dou 3 a 2. Similarly, f 1 3 equal to dou 1 a 3 minus dou 3 a 1 and f 1 2 is dou 1 a 2 minus dou 2 a 1. Together, we can write f mu nu as dou mu a nu minus dou nu a mu, where dou mu is dou by dou t minus gradient, a mu is 0 phi and a. What about the Maxwell's equations? Dou mu f mu nu is equal to j nu. So, that will give, taking the derivative of f mu nu written in terms of a nu and a mu, we have dou mu a nu minus dou nu a mu equal to j nu. This is nothing but dou mu acting on a nu minus dou nu acting on dou mu a mu equal to j nu. So, the Maxwell's equation written in terms of the potential in general looks like this. Now, let us come to something very interesting, partly something which we already know earlier from our elementary electrodynamics discussions. If you consider the expression for the electric field, when we consider the expression for the electric field E equal to minus grad phi minus dou by dou t of A. If I take a mu and make a change in it to a prime mu, which is actually equal to the original a mu plus for derivative of some scalar field. So, chi is some scalar field and or scalar function, in this case chi is some scalar function. In that case, we have E prime equal to, so essentially this change in A mu will, sorry, it should have been A mu, phi will go to phi plus time derivative of chi, and A goes to original A plus gradient of phi, A minus grad chi, because gradient has a relative minus sign compared to the normal contravariant vectors. So, this will tell me that I have a gradient of phi plus time derivative of a scalar function minus time derivative of original A, 3 vector A, minus gradient of chi, and this is equal to minus grad phi minus derivative of grad chi minus dou by dou t of A minus of minus plus dou by dou t of grad chi, which is equal to the original E, because the second and the fourth terms are exactly the same excepting that their signs are different. So, bottom line is that if we change A mu to A mu prime, which picks up derivative of a scalar field in addition to the original A mu, then the electric field remains the same. How about the magnetic field? Magnetic field B is equal to curl of A, which is equal to curl of, or B prime now is equal to curl of A minus grad chi, which is equal to curl of A minus curl of gradient of chi, and curl of a gradient of any function, any scalar function is going to be equal to 0, is equal to 0. It is a property of the curl of a gradient. So, this is equal to curl of A, which is nothing but the original B. So, B and A are invariant as A goes to A plus for gradient, 4 dimensional gradient of a scalar function chi. Electric field is not changed, magnetic field is not changed. So, there is a freedom in choosing the potential A mu. You cannot change the different components of A mu independent of each other arbitrarily. If the change in A mu is in this fashion, that A mu goes to original A mu plus a 4 gradient or dou mu of a scalar function, any scalar function denoted here by chi, then the physical electric and magnetic fields are not changed. So, if we consider the case where electric and magnetic fields are measurable and therefore physical quantities, then A is not uniquely fixed for a given E and B, or we cannot directly attribute therefore any physical meaning to A mu. Actually, that is not exactly the way we interpret. We will say that there is some arbitrariness in A mu. So, to physically interpret it as anything, we have to remove these unwanted degrees of freedom. But this particular freedom or arbitrariness in the potential is very important in particle dynamics. We call this the gauge transformation. This particular way of changing A mu to a new A mu is called gauge transformation. And we see that the electric and magnetic fields are invariant under such gauge transformation. So, we can say physics is invariant under such gauge transformation. This is going to be a very important point to note when we come to the dynamics of the particle in quantum field theory. So, what we will do is to see how to remove the unwanted degrees of freedom in A mu and try to fix this, so that later on when we give physical meaning to this A mu, we have physical quantities without any arbitrariness in it. There are different ways to do that. So, let us look at one way of doing it. Consider A mu. So, it has 4 components: phi, A x, A y, A z. When we say these are not uniquely fixed, we can actually think about some relation between these quantities that will try to fix this thing. Let us consider the 4 divergence of A mu. For any arbitrary choice of A mu, it is not guaranteed that dou mu A mu is equal to 0. But let me start with some potential which I denote actually by A mu prime or A prime. Divergence of that is not equal to 0. But then I make a transformation to A mu which is equal to A prime mu plus dou mu chi, where chi is some scalar field, scalar potential, scalar function. Take the derivative of A mu, that is a derivative of A prime mu and dou mu of chi. Now, we can choose chi so that dou mu chi is equal to minus dou mu A prime mu. Since this transformation is allowed for any scalar field, let us say we can choose some field, any scalar function chi. Let us choose a scalar function which satisfies the condition dou mu chi is equal to minus dou mu A mu prime. That will then give us dou mu A mu equal to 0. So, we can always choose some scalar function to set the potential with which is divergenceless. To start with, if it is not divergenceless, then we can always consider the scalar field which will give us the, which will change the A mu so that the new A mu is divergenceless. We have an A mu which satisfies this condition. Is that the only arbitrariness in that? That is not. If we further make any change to some A mu plus divergence A mu plus dou mu lambda, where lambda is some other scalar field. This scalar field cannot be completely arbitrary, because in that case the 4 divergence of A mu may not be equal to 0. But if we take dou mu A mu of lambda to be equal to 0, or if we choose lambda so that dou mu A mu lambda equal to 0, then so this is by choice, okay, so that this is equal to 0. This will give us dou mu A mu going to dou mu A mu plus dou mu lambda, which is equal to dou mu A mu plus dou mu dou mu lambda, which is equal to dou mu a mu, because the second term is equal to 0. That is a property of the chosen lambda. So, we can fix this in this fashion. So, after fixing a mu, so that the for divergence equal to 0, there is still some arbitrariness in that, and that arbitrariness is that we can again add a dou mu lambda, so that dou mu of lambda is equal to 0 without changing the electric and magnetic fields. Okay. So, the electric and magnetic field or the physics remains the same still. Okay. So, we will come to this gauge freedom and how the Maxwell's equations are written within this, and tell a little more about the gauge conditions that we have just now mentioned or discussed in the next discussion.